а потом, может быть, туда выложить. Так что...
Вот так можно.
Да. И здесь.
Вот. Okay, today our first goal will be to prove the inversion formula, which was stated at the end of the previous lecture. The Fourier inversion formula. Well, let's recall the statement. As usual, we have a locally compact abelian group G. And as usual, we assume that it is second countable. We equip it with a power measure, U. And we denote by B1 or G the intersection of the Fourier Stieltjes algebra of G, B of G, and O1 of G. So let's recall that B of G is, by definition, the image of the measure algebra of the dual group under the Fourier transform. Well, more exactly, under the dual Fourier transform. So this is the definition of B of G, and we intersect it with L1 of G. So far, this is just a vector space. Well, in fact, it will follow from the inversion formula that this is not only a vector space. This is an algebra under two different products. This is an algebra under the pointwise product and under convolution. But this is not essential at this point, so we look at B1 of G just as a vector space. And then we have the following result for the inversion formula. First of all, if f sits in B1 of G, then the Fourier transform of f is integrable, so it sits in L1 of the dual group. And second, there is a unique hard measure on the dual group that's denoted by mu g hat, such that for every function f in B1 of G, we have the full inequality. So if we apply the Fourier transform to f, and then apply the dual Fourier transform, which makes sense because f hat is integrable, so we can apply the dual Fourier transform. Then we obtain the same function f up to reflection. So S of f is the function which is given by the following formula. So more explicitly, this can be written as follows. F of x is the integral f hat of chi of x d mu of chi. So formally I have to put x inverse here because of this s. Instead of that, I put the complex conjugation here, and this is equivalent. And this is true for every x in G. Listen, actually, this is not the final form of the inversion formula. It can be a little bit generalized, and we will discuss it a bit later after the projective duality. The measure mu g hat, which appears in this formula, is called the dual of mu g. mu g hat is the dual of mu g, or the Close-Shadowed measure on g hat. Well, in fact, of course, we already know that g hat is also a locally compact billiard group, so there is a higher measure on g hat, and it is unique up to a multiplicative constant. So if we choose an arbitrary higher measure on g and an arbitrary higher measure on g hat, then we will have this formula up to a multiplicative constant. But of course, if we choose this constant in a suitable way, then we'll have an exact quality. So at the end of the previous lecture, we considered some examples of dual measures for some classical groups. And today we'll discuss the proof of the inversion formula. Before we discuss the proof, let's briefly look at the strategy of proof. Well, of course, we already know that there is a higher measure on g hat. However, it turns out that the pure knowledge of this fact gives us nothing useful for the proof. And moreover, it seems that all known proofs of this result, and actually there are many of them, there are many proofs of this formula, but almost all known proofs involve a construction of this measure from scratch. And the guiding principle in this construction is not the left invariance of this measure, but rather the inversion formula itself. So in summary, what we want to do is to construct a positive Radon measure on g hat satisfying this formula. And the left invariance of this measure will come as a byproduct of the construction. So this is different from our original construction of the higher measure. When we constructed the higher measure, we tried to do it in such a way that this measure is left invariant. And here we do it in a different way. We are trying to find the measure satisfying this formula, and the left invariance will be automatic. So let's look at this formula once again. So if we want mu g hat to satisfy this formula, then in particular, this formula has to be satisfied at the identity of the group. So we want to construct mu g hat in such a way that the following relation holds. We may try to define this. Of course, we know that positive Radon measures are positive functionals on completely supported continuous functions. So we may try to define the measure mu g hat exactly by this formula. But the problem here is that the functions of the form f hat they don't span they don't generate the space of continuous compactly supported functions. So the set of functions of the form f hat, where f runs over b1 of g, is not the same as the space of continuous compactly supported functions on g hat. And this shows that in general we cannot use this formula as a definition of this measure. In fact, the inversion formula rather easily implies that this set is precisely b1 of g hat. So the Fourier transform takes b1 of g bijectively onto b1 of g hat. But in general, a function in b1 is not necessarily compactly supported. And conversely, not every compactly supported continuous function sits in b1. So this is not contained in here, and this is not contained in here. They are different. So the idea of simplifying this formula is as follows. we try to somehow regularize this formula by replacing f by the convolution of two functions in B1 of G. So we want to construct the measure mu such that the following convolution is equal to the integral of the Fourier transform of the convolution. And we know that the Fourier transform of the convolution is the pointwise product of the Fourier transforms. So we want this formula to hold. The advantage of this approach is that this expression, that is the product of the higher measure we are looking for, by the Fourier transform of G, turns out to be a finite complex Radon measure. So more exactly, we will see that there is a complex Radon measure nu G on the dual group such that this convolution evaluated at the identity is the integral of f with respect to the measure mu G. And after we find such a measure nu G, when we try to define, and I put the quotation marks here because there is a rather informal idea, when we try to define our measure mu G hat by the following informal equality, this is mu G divided by the Fourier transform of G. Anyway, this looks reasonable because of if we compare this and this. Of course, after we construct such a measure nu G, we have to make a precise sense of this equality. Then we have to show that this doesn't depend on the choice of G, and to show that this measure is indeed a left invariant positive Radon measure, and then to eventually to prove the inversion formula. But anyway, this will be our strategy. So we will use the advantage of the electronic blackboard, and we'll come back to this strategy several times during the proof. Okay, so the proof itself will be divided into several lemmas. Some of the lemmas will be rather straightforward, and I'll leave them as exercises for you. Lemma 1, lemma exercise 1, gives us some simple algebraic properties of the Fourier transform. First of all, the Fourier transform commutes with S, commutes with our reflection map. Such an equality. And there is a similar equality for the dual Fourier transform. Property 2 is that if we apply a left translate to a complex Radon measure nu and take the Fourier transform, this will be equal to the product of the Fourier transform of nu by the evaluation character epsilon x for every Radon measure mu on G. And we have a similar formula for the dual Fourier transform. If you take a Radon measure on the dual group, apply the left translate, and take the dual Fourier transform, then the result will be the product of the same character chi by the dual Fourier transform of mu. Here mu is a measure on the dual group, and chi is a character. And property 3, what happens if you multiply measure by a character and then apply the Fourier transform? Well, we will get the left translate of of the Fourier transform by the inverse character. And we have a similar formula for the dual Fourier transform. You can multiply a matter on the dual group by the evaluation character epsilon x and apply the dual Fourier transform. We'll get to the left translate by the inverse element of u, of the Fourier transform of u. Actually, such formulas were already discussed in the context of finite groups on the first lecture. Not, they hold for an arbitrary local compact abelian group, and the proof is absolutely straightforward. Just a little calculation. Actually, property 2 is immediate from the fact that the left translate is the convolution by the Dirac measure delta x, and that the Fourier transform is an algebra homomorphism. So these two formulas follow from the multiplicative property of the Fourier transform. And this is an explicit, simple explicit calculation. As a corollary, we see that the Fourier Stieltjes algebra, B of G, is stable under reflection, under S, because of property 1, under translations. This follows from this formula. Oops. And it is also stable under multiplication by characters, and this follows from this formula. Under multiplication by unitary characters. Lemma 2, lemma exercise 2, gives us some useful properties of the convolution. First of all, I claim that if f belongs to L1 of G, and G belongs to L infinity of G, then their convolution, f star G, is defined everywhere on G, belongs to space of bounded continuous functions, so it is continuous and bounded, and its supremum norm is less than or equal to the product of the L1 norm of f and the L infinity norm of G. So we can always convolve L1 function and an L infinity function. Let's now take two functions in L2, f and g, in L2 of g. So I claim that if we convolve f and sg, then this function is also defined everywhere on G. It belongs to C0, so it is continuous and vanishes at infinity. So compare, here we have continuous and bounded, and here it vanishes at infinity. And the supremum norm, not G, but SG here, SG. Actually, maybe you have already observed that since G is abelian, we can easily replace here G by SG by G, because if G is abelian, more generally, if G is unimodular, then L2 of G is stable under S. In general, this is not true, but for unimodular groups, we can replace SG by G, and we have the same result. But for convenience, I write SG here. This is also convenient for the proof. So the supremum norm is dominated by the product of the L2 norms of f and g. And finally, property 3, if f sits in L2 of g, then the convolution of f and SF complex conjugate, which is by property to defined everywhere. This function is positive definite. Let me give you some hints for the proof. I hope you'll be able to reconstruct the details rather easily, but nevertheless, what is essential here, if you write explicitly the formula for the convolution in case 1, it will be convenient to write it in the following way. This convolution evaluated at x is this is SG multiplied by the left translate of f, and we integrate over the group. This can be easily deduced from the definition of the convolution. So this function sits in L infinity because G is in L infinity. This one sits in L1, and so the integral exists because the product of a function in L infinity and in L1 is integrable. So this exists for all x, and moreover, if we try to estimate the absolute value of this integral, clearly it will be less than or equal to the right-hand side of this formula. So this equation, this equality, implies that this function is defined everywhere, is bounded, and satisfies this property. So the final point, why is it continuous? We have to prove that it is continuous. The continuity of this function, can easily be deduced follows from the continuity of the map, which takes x to the left translate of f. Some time ago, we proved that this map is continuous from G to L1 of G, and this map is already it already appears in this formula. So the continuity of this map readily implies the continuity of the convolution. So this is a hint to part 1. As for part 2, the fact that it is defined everywhere and satisfies this estimate is proved in a similar way by writing such an integral of this form and by using the Pirkovskii formula. Why is it in C0? Well, let's look at the following diagram. First we prove that the following map is defined, so it takes, this is not correct. It takes f and g to the convolution of f and sg. So the resulting function is bounded and defined everywhere. So we have a bilinear map from here to here. And we want to show that its image sits in C0. But if f and g are continuous and compactly supported, then the respective convolution is also continuous and compactly supported. The continuity is proved by the same argument as here, and the fact that support is compact is immediate from the formula for the convolution. So it is also continuous and compactly supported. In particular, it sits in C0. But C0 is a closed subspace in L infinity. And continuous compactly supported functions are dense in L2. So this is dense. And this diagram shows that since this is dense in here, it follows that the whole space L2 cross L2 goes to the same closed subspace that is to C0. Okay, so this is a hint to part 2. Part 3 is absolutely straightforward. Just use the original definition of a positive definite function, write the respective quadratic form, and the little calculation shows that it is. It can be expressed in terms of, Well, anyway, no comments. Just a simple calculation. You'll see that it is very easy. Okay. Well, this is lemma 2. Lemma 3 is also very easy. Lemma 3. Lemma exercise 3. If f is a positive definite function on G, and chi is a unitary character, then the pointwise product of chi and phi is also positive definite. And again, the proof is absolutely straightforward. Just write the original definition of a positive definite function, and you'll see that you'll automatically see that this function is positive definite. By the way, a little remark is that lemmas 2 and 3 hold for non-abelian groups as well. And the proof is the same. The proof is exactly the same. Okay. Now lemma 4. Lemma 4. Basically the meaning, well, first of all, let me give you a statement and then explain, I'll try to explain the meaning. I claim that for every compact subset K of the dual group G you had, we can always find, probably it will be useful to introduce some notation here. So let's denote by P C of G the set of compactly supported positive definite functions. The set of compactly supported positive definite functions. The support of phi is compact. So lemma 4 states that for every compact subset K of the dual group, we can always find positive definite compactly supported function f on G such that its Fourier transform is non-negative and such that it is strictly positive on K. Strictly positive on K. So roughly the meaning of the lemma that we have many such functions, many compactly supported positive definite functions in the set that we can always choose them in such a way that the Fourier transform will be strictly positive on K. In fact, the first inequality is not very surprising here. We will be able to deduce, easily deduce from the inversion formula that if f is positive definite, if f is any positive definite function, then its Fourier transform is always non-negative. So what is essential here, so the crucial point here is that it will be strictly positive on K. So this is the main point of this lemma. Well, let's try to prove it. To begin with, we choose take any continuous compactly supported function h on G such that the integral of h is not 0. Of course, there are many such functions, so we take any of them, and we observe that this integral is nothing but the Fourier transform of h evaluated at the identity, just by the definition of the Fourier transform. Let now G denote the convolution of h and h star, where h star is the involution in L1 of G. So let's recall that the involution in L1 of G is given by the following formula. So what can we say about G? Lemma 2 implies that G is positive definite. just look here. This special case of this property. So it is positive definite. Moreover, it's easily seen to be compactly supported because H is compactly supported. The Fourier transform of G, well, the Fourier transform of the Fourier transform is a star homomorphism, so it is the product of H hat and the complex conjugate. That is, this is just the square of the absolute value of H hat. So it is non-negative. It is non-negative. And if we evaluate at the identity, well, this is H hat evaluated at the identity squared. This is strictly positive because this is non-zero. So strictly positive. But G hat is continuous. So it will be strictly positive in the neighborhood of the identity. There is a neighborhood V of the identity in the dual group such that G hat is strictly positive on V. Now let's look at our compact set K. So K is compact, and so it can be covered by finite and many translates of V. So we can always find finitely many points, chi1 to chi_n, in G hat, such that K is covered by their translates. And let's now construct our function f. Let's define f by the following formula. So we multiply G by chi and then take the sum from 1 to n. So what can we say about this function? Well, lemma 3 implies that it is positive definite. So we multiply a positive definite function by a character, we get a positive definite function, and of course the sum of finitely many positive definite functions is positive definite. So it is positive definite, and of course it is compactly supported, because each of them is compactly supported. Now, if you take the Fourier transform of this function, so this is given by lemma 1, we know that the Fourier transform of the product by character is the left translate of the Fourier transform. So the Fourier transform of f is the following sum. Now we see that every summand here is strictly positive on the respective translate neighborhood here. So every summand is non-negative, and so the whole sum will be strictly positive on K. Because K is covered by the respective sets. And this completes the proof of lemma 4. Okay. Well, this was a preamble. Now let's turn to the main part of the proof. Actually, the main part, you will see that the main part of the proof will be essentially algebraic. So essentially all analysis in the proof of the inversion formula is here. So let's introduce, first of all, let's introduce the following notation. For every function f in V1 or G, we define a complex element measure nu f on the dual group as follows. It is the unique complex element measure whose the dual Fourier transform is equal to SF. This is well defined, and such a measure exists, and it is unique. It exists because the Fourier CLTS algebra is stable under S. So SF also sits in B1. In particular, it sits in the Fourier CLTS algebra. And know that the Fourier TS transform, the dual Fourier transform is injective. So it maps the measure algebra on G hat bijectively onto the Fourier TS algebra. So such a measure is unique. It exists and it is unique. So why is it reasonable to consider such a measure? A short remark which explains why it is reasonable. Let's recall that our goal is to prove the Fourier inversion formula. That is to prove that SF equals F transform, and then we apply the dual Fourier transform. This is our goal. And we have defined mu F in such a way that SF is the dual Fourier transform of mu F. So if we believe in the inversion formula that we are trying to prove, then by comparing these two equalities, we see that actually mu F is equal to the Fourier transform of F, or more exactly, the Fourier transform of F multiplied by the dual measure. As usual, we identify L1 with a subspace with an ideal in the measure algebra consisting of absolutely continuous measures with respect to the Harmonic measure. So this measure mu F that we've just defined is actually, it satisfies this formula. Of course, so far we don't, the mu G hat is undefined. But if we believe in the inversion formula, then we will have this equality. And if we come back to our strategy once again, look here. So this our definition of nu G is the exact meaning of this formula. So nu G is G hat multiplied by the higher measure we are looking for, exactly as we want in this informal equality. Okay, so our next lemma gives us some useful properties of such measures mu F. First of all, if you take an arbitrary function, integrable function h on G, then the integral of its Fourier transform with respect to mu F, so F is an arbitrary function in B1 of G. So the integral of this function h hat with respect to mu F, of course this is well defined because mu F is finite, it's a finite complex level measure. We can integrate any continuous bounded function. In particular, we can integrate h hat. So this integral, by the way, well, let me write this explicitly. So this notation means that we take the integral of h hat with respect to this measure. So this is equal to the convolution of h and f, and then evaluated at the identity.
Скажите, пожалуйста, как здесь играет то, что f с волной, она больше нуля на компакте?
F с волной кто такая?
Вот мы же построили эту функцию, вот, в смысле, точнее, в смысле, крышка, преподавание
Вот
Фурье.
это. Пока никакой.
Все.
Кто-то здесь утверждает, что она существует. Пока это лемма еще не сыграла никакой роли, она потом сыграет. So far we haven't used the lemma form. It will be useful later, but here f is an arbitrary function in L1, not necessarily in B1, sorry. It is not necessarily positive definite. It's in B1, so it can be expressed as a combination of 4 positive definite functions, but it is not necessarily positive definite itself. So I claim that we have this formula, and again, this is predictable. This is quite predictable because of this. So if we look here, we see that we want to construct mu G in such a way that this formula holds. And this is exactly our lemma 5. And the second part of lemma 5 states that for any two functions f and g in B1, we have the following equality. And this is the precise meaning of the fact. Let's come back once again to our strategy. This is the precise meaning of the fact that this informal definition doesn't depend on the choice of G. So roughly, this formula has an exact meaning, but roughly it means that nu G divided by G hat equals nu F divided by F hat. Okay. Now let's try to prove this result. Well, let's look at the left-hand side. H hat, the integral of H hat with respect to nu F. So this is the integral of H hat with respect to nu F. H hat is the Fourier transform, so it is the following integral. This is the Fourier transform of H, and then we have to integrate with respect to nu F over dual group. We can now interchange these two integrals by using the Fubini theorem. Formally, nu F, of course, nu F is a complex matter. So why is it possible to use the Fubini theorem for complex matters? Well, it is indeed possible because every complex matter is a combination of 4 positive matters. So this implies that Fubini's theorem holds for complex matters as well. So we interchange the order of integrations. So what we get, the integral over chi over by the measure nu F. So we integrate chi, and this is precisely the dual Fourier transform of nu F. So we get nu F check of x, and then integrate over G. But nu F check is SF by definition. So the result is the integral h of x, f of x inverse. But this is just the convolution of h and f evaluated at the identity, just by the definition of the convolution. And this completes the proof of part 1. To prove part 2, we do the following. So we have 2 measures on the dual group. We have to show that they are the same. And to show that they are the same, we integrate the Fourier transform of an arbitrary function in L1. So we take a function h in L1 of G, and we integrate its Fourier transform with respect to, say, the first measure, f hat nu G. Well, by the definition of this measure, what is the product of a measure by a function? This is the measure which is given by the function which integrates the product of this function by f hat, simply by definition of the product of a measure by a function. So this is the integral of the product h hat f hat with respect to nu G. The product of the Fourier transforms is the Fourier transform of a convolution. So we have the following nu G. And now we use part 1. And by part 1, this is the convolution of what? HF, and we take the convolution of this function with G, and then evaluate at the identity. Well, the group is abelian, so the convolution is commutative, and it is always associative. So by the commutativity and the associativity of the convolution, we can reorder the functions as follows. So basically, we just interchange G and F. And now looking back at this chain, So we can also interchange them here, and we get the following expression. So we see that these two measures have the property that the integral of any function of the form h hat with respect to these measures, so the integrals are the same. The integrals are the same. But on the other hand, we have the density theorem that which says that the Fourier image of L1 is dense in C0 of the dual group. So these two functionals, if we look at these measures as functionals on C0, so they agree on this dense subspace, so they are the same. So this shows that these two measures are the same. And this completes the proof of lemma 5. Lemma 6. This is almost our final step in the proof of the inversion formula. Lemma 6 tells us something about left translates of the measures nu f. So why is it reasonable to look at left translates of nu f? Let's come back again to our strategy. So we want to define our measure by this formula. So mu g has to be left invariant. It has to be left invariant. So when we will prove the left invariance of mu g, it will be helpful to know something about left translates of the measures mu g. So the left translate of the measure of this measure can be described as follows. This is our lemma 6. Lemma 6. The left translate of mu f is the measure u corresponding to the function chi inverse f. So we simply multiply f pointwise by the inverse character for every f in V1 and for every character. The proof is very easy. So they are measures of the dual group. We know that the dual Fourier transform is injective. So it's fastest to show that the dual Fourier transforms of these measures are the same. Well, let's calculate the dual Fourier transform on the left-hand side. Here we use lemma 1. So the dual Fourier transform of the left translate is just the product of the dual Fourier transform by the respective character. This function mu f check is by definition SF. And since chi is unitary character, it's easily seen that this is the same as S applied to chi inverse f. But this is again by definition equal to nu chi inverse f check. And this is the end of the proof. So we have proved that the dual Fourier transforms of these two measures are the same. So they are the same because the dual Fourier transform is injective. Okay, so let's now turn to the proof of our inversion formula, proof of theorem. So we want to define a measure, a higher measure of the dual group. This will be a positive functional or continuous compared to supported functions. So let's define this functional. We define a functional I on the space of continuous compared to supported functions on G hat as follows. So we take a continuous compared to supported function psi on G hat, and we choose by using lemma 4 a positive definite compact to supported function f on G such that its Fourier transform is non-negative, and such that its Fourier transform is strictly positive on the support of psi. So this is where we'll use our lemma 4. The support of psi is compact, so lemma 4 tells us that such a function exists. And we'll let I of psi equal the integral of psi divided by f hat with respect to nu f. Of course, we can integrate because f hat is strictly positive on the support, so the function psi divided by this Fourier transform is well defined and continuous at compact support. And we simply integrate it with respect to this measure nu f. Of course, we have to prove that this doesn't depend on f, otherwise such a definition will be useless. Let's show that this expression doesn't depend on f. Well, indeed, if we have another such function, say g, ug is another such function, which is whose Fourier transform is strictly positive on the support on psi, then this integral, let's write it once again. We integrate this function over g hat with respect to nu f. So we can divide this function by g hat as well. And to get the same expression, we multiply the measure nu f by g hat. Clearly, this is the same. And now we use lemma 5. By lemma 5, this measure is equal to f hat nu g.
Что происходит у этого отношения вне носителя пси?
0.
Просто f с крышкой тоже же может быть 0? Или...
Ну что? Просто носитель-то, смотрите, вот, конечно, какая-то общая топология, она очень простая. Вот носитель — это компакт.
Это да.
Здесь у нас есть пси. Вот такая вот какая-то. А f с крышкой, она здесь положительна. Ну а дальше она может быть, конечно, тоже где-то 0. Вот это пси. А это f с крышкой. Но делить можно. На компакте мы просто делим, а вне его будет 0. И это непрерывная функция будет. Ну, упражнение по общей топологии. So it's an exercise in general topology to show that this function is continuous and compactly supported. The continuity is maybe not immediate, but it's very easy. So this picture represents how psi and f hat are related. The point is that f hat is strictly positive on the support of psi. And this implies that this psi over f hat is continuous. Okay, so this measure is multiplied by f hat, the function is divided by f hat, so this is the same as the integral of psi over g hat with respect to the measure nu g. And as a result, we see that this expression doesn't depend on the choice of f. Basically, this is the precise meaning of, let's look once again now at strategy. This is the precise meaning of this informal definition. Of course, formally we cannot divide measure by a function which is somewhere 0, but we can do it somehow pointwise. That is, we want to integrate continuous compactly supported functions, and each time we choose a suitable function g hat such that the respective integral exists. Okay. Now, since this definition doesn't depend on the choice of f, it's obvious that I is linear. Clearly, I is linear. because if we have two functions, say psi1 and psi2, we can choose a common f, which serves both, which works for both for psi1 and for psi2. The union of their supports is compact, so we can choose the same f for two functions, and this implies that I is linear. Also, it is positive, because so we know that f is positive definite. F is positive definite. Oh, sorry, this is, of course, this is true, but we also know that f hat is non-negative. F hat is non-negative everywhere. And also, f is positive definite. And since f is positive definite, it follows that the respective measure, nu f, is positive. Let's call that the dual Fourier transform. This is Bochner's theorem. The dual Fourier transform is a bijection between positive measures, positive finite measures on G hat, and positive definite functions on G. So nu f is also positive. And these two facts together imply that our functional I is positive. Okay, now I claim that for every function f in B1 of G, the product of f hat by I is equal to the measure nu f. At the first glance, this seems to be equivalent to our definition of I, but not exactly, because in the definition of I, the function f was not arbitrary. It has some special properties. It is continuous, compactly supported, and its Fourier transform has such properties. So I claim that this formula actually holds for any function f in B1. And this is also easy to see by using the definition of I. Well, indeed, for every continuous compactly supported function psi on the dual group, the left-hand side, f hat I, applied to psi, what is this? So by definition, this is I applied to the product, f hat psi. This is our definition of the product of a linear functional by a function. And by construction of I, this is the integral of f hat psi divided by g hat with respect to nu g for a suitable positive definite function g. So we remember that g is chosen in such a way that it is strictly positive on the support of this function and non-negative everywhere. G hat is strictly positive on the support and non-negative everywhere. Now we can write this in the following equivalent form. We integrate psi over g hat with respect to the measure f hat nu g. This is the same. But again, now by using lemma 5, we see that we can interchange f and g here. By lemma 5, we see that this is equal to the following: g hat nu f. And of course, this is nothing but the integral of psi with respect to nu g. Nu f, the integral of psi with respect to nu f. And so we get this formula. Let's denote it by star. Okay. By the way, this formula also implies that I is non-zero. So we want, of course, we want a non-zero functional. So this formula, in particular, it implies that I is non-trivial. This is clear because well, if f is non-zero, then nu f is non-zero. The dual Fourier transform is bijective, and it takes non-zero measures to non-zero functions and the other way around. So if f is non-zero, then this is non-zero, and so I is necessarily non-zero. Okay, now we want to show that I is left invariant. Well, indeed, let's take a character I, according to the dual group, and let's calculate the left translate of I. So we apply this function to an arbitrary continuous compactly supported function psi. So this is by definition I applied to the left translate of psi by the inverse character, by the definition of the left translate of the functional. We have this formula. Now we use the definition of I, and we see that this is the integral of this function divided by suitable f hat with respect to the measure nu f for a suitable positive definite compactly supported function f on G. So we choose f in such a way that its Fourier transform is strictly positive on a large compact set. Actually, we choose this compact set in such a way that it covers the support of psi and the support of this translated psi. So what is this? So first of all, let's write this function in a slightly different way. L chi inverse applied to psi divided by L chi f hat. So clearly this is the same. Now let's use the definition of left translate of a measure. So by definition of the left translate of a measure, this is the integral of this function in brackets here with respect to the translated measure uf. L chi uf. Again, by the definition of the left translate of a measure. Now, what is this? First of all, the left translate of the Fourier transform by lemma 1, here we use lemma 1, the left translate of the Fourier transform is the Fourier transform of the product of f by the inverse character, chi inverse f hat by lemma 1. And by lemma 6, the left translate of nu f is the measure nu associated to chi inverse f by lemma 6. So we see that this is actually the definition of I of psi. Because here and here we have the same function. So by looking here and here, we deduce that I is left invariant. I is left invariant. Okay, so we get our measure. So now we have a positive random measure. Actually, it is a higher measure. We have a higher measure. It is left invariant because I is left invariant. We have a higher measure mu g hat on the dual group, such that I is the integral with respect to this measure by the Rees-Markov-Kaputani theorem. Finally, we have to show that this is exactly what we are looking for. if we now look at this relation star, we see that the product of f hat and our measure mu is equal to nu f. So we simply write this in terms of measures. And we see that f hat times mu g hat equals mu f for every f in B1 of G. Well, it's simple exercise in measure theory to show that a similar formula holds for the valuation of nu f. So nu f is absolutely continuous for our measure, and f hat is the density of this function, of this measure. So what is about the variation of nu f? It is also absolutely continuous, and the density is the absolute value of f hat. So the absolute value of f hat times mu g equals the variation of nu f. But the variation of nu f is finite. This is a finite measure. And so this implies that f hat is integrable with respect to mu g. Mu g hat. Sorry, I forgot the hat here. This function is integrable. And this gives us the first part of the inversion formula. So f for every f in B1, its Fourier transform is integrable. And let's now calculate the dual Fourier transform of f hat. I want to show that this is equal to SF. Well, about the definition of the dual Fourier transform, it is the following integral: f hat of chi of x d mu g hat of chi. This is just the definition of the dual Fourier transform. But the product of mu g by f hat is equal to nu f. So this is simply the integral of chi with respect to mu f. That is, this is nothing but the dual Fourier transform of nu f. And the dual Fourier transform of nu f is, by definition of nu f, this is SF. Yeah, this completes the proof. This is our inversion formula. Okay. So what next? Just trying to finish. Actually, this formula very easily implies the Planck-Schreier theorem. So if you don't mind, I think it will be I'll just maybe 5 minutes to prove the Planck-Schreier theorem, because actually it's indeed a simple corollary of the inversion formula. So from now on, we adopt the convention that both G and G hat are equipped with our measure, with our measures mu g and respectively mu g hat in such a way that mu g hat is dual to mu g, such that mu g hat is dual to mu g. That is, in such a way that the inversion formula holds. And we have the following result, which is basically an abstract version of Planck-Schreier theorem. Well, again, it is usually referred to as Planck-Schreier's theorem, but in fact, Planck-Schreier himself proved it for the real line. And this abstract version is actually as similar to the inversion formula, is due independently to Andrei Weil and Dmitry Abramovich Raykov. The Fourier transform, first of all, if we restrict the Fourier transform to the intersection of L1 and L2 of G, it takes it to L2 on the dual group. And moreover, f restricted to L1 and L2 uniquely extends to a unitary isomorphism, that's denoted by f dot between L2 of G and L2 of G hat. This result also explains why the Plancherel measure is so called. It is the unique Harmonic measure on G hat which satisfies the Plancherel theorem. If we multiply mu G hat by a constant, then this map will not be unitary, but it will be unitary up to a constant. And the proof is a simple application of the inversion formula. First of all, we show that the Fourier transform restricted to the product, to the intersection, of L1 and L2, indeed takes it to L2, and moreover it is isometric for the L2 norm. Well, indeed, if we take function f, which sits in the intersection of L1 and L2, let's look at f, the convolution of f and f star. What can we say about this function? On the other hand, this function sits in a 1, because it is the convolution of two functions in a 1. But on the other hand, it is positive definite, because value of 2. It's the convolution of f and f star, and f is in L2, so value of 2. It is positive definite. In particular, it sits in B1, and so the inversion formula applies to this function. Let's apply the inversion formula. The inversion formula implies that this function, in particular, we can evaluate it at the identity, is equal to the integral of its Fourier transform over the dual measure. This is a special case of the inversion formula of the Fourier transform. Well, the Fourier transform of this function the Fourier transform is a star homomorphism. So this is nothing but the absolute value of f hat squared. And on the other hand, if you write the definition of the convolution explicitly, we see that the left-hand side of this formula is nothing but the integral of f squared over g. And we see that, first of all, f indeed takes the intersection of L1 and L2 to L2. And moreover, f restricted to L1 and L2 is isometric, is an isometry with respect to the L2 norms, here and here. Since this intersection is dense in L2, actually continuous compactly supported functions are already dense in L2. So this intersection is also dense in L2. Since it is dense, it follows that this map uniquely extends to an isometry that's denoted by f dot from L2 to L2. Well, not f itself, but rather f restricted to L1 and L2. Because in general, L1 is not contained in L2, and L2 is not contained in L1. So we first need to be restricted to this intersection and then extend it to an isometry from L2 to L2. So to complete the proof, we have to show that this extended map is surjective. Well, if it is not surjective, then its range is a proper closed subspace of L2. And to show that this subspace is not proper, it is equal to F2, to L2, we have to show that the orthogonal complement is trivial. Well, let's suppose that psi is a function in L2 such that psi is orthogonal to the range of F dot. For convenience, I replace here psi by the complex conjugate, which is also in L2. So we assume that the complex conjugate of psi is orthogonal. And we have to show that psi, we want to show that psi is 0 almost everywhere. Well, psi is orthogonal to this subspace. In particular, it is orthogonal to Fourier transforms of functions in the intersection of L1 and L2. And of course, if this intersection of L1 and L2 is stable under left translates. So this implies that psi complex conjugate is orthogonal to the Fourier transform of the left translate of every function f in the intersection of L1 and L2. So let's write this down explicitly. The integral of the product is 0. The integral of the product is 0. So the product of this function and the complex conjugate of psi bar, so the complex conjugate will be just psi. The Fourier transform of the left translate is the product of f hat by the respective evaluation character, epsilon x f hat psi. Let's look at this product, f hat and psi. Psi sits in L2. F hat so also sits in L2 because of this. The product of two functions in L2 sits in L1. This sits in L1. And what is this? This is nothing but the dual Fourier transform of this function f hat psi, the dual Fourier transform evaluated at x. And this is true for every x in G. So this function is identically 0. And since the dual Fourier transform is injective, it follows that at psi is 0 almost everywhere on G hat, because the dual Fourier transform is injective. And this is true for every f. This is true for every f in the intersection of L1 and L2 of G. Now we use our lemma 4 again, which tells us that we can always choose f in such a way that for every compact subset of G hat, we can always choose f hat in such a way that its Fourier transform is strictly positive. In particular, it is non-zero on the respective compact set. And since this compact set was arbitrary, we deduce that psi is 0 almost everywhere on G hat. Here we implicitly use the fact that G hat is second countable, and in particular sigma compact. So psi vanishes on almost everywhere on every compact subset, but G hat can be represented as the union of countably many compact sets, and so psi is 0 almost everywhere. And that's it. So this shows that psi dot takes L2 of G onto L2 of G hat. And this is the end of the proof. Okay, so in conclusion, just a few remarks. I'll not write anything, just a few remarks about the Pontryagin duality. This is an important result, which unfortunately we didn't have time to prove it at the lectures. So I'll just make a few comments. So I hope you remember the statement. We have a canonical map IG from G to the second dual, which takes every x to the expected evaluation character. And the Pontryagin duality tells us that this map is a topological isomorphism. Pontryagin duality, or more exactly, Pontryagin and one content duality. Pontryagin proved this for second countable groups, one content did it for arbitrary locally compact abelian groups. So the original proof given by Pontryagin and by one content was essentially based on the structure theory of locally compact abelian groups. And later, Gerfand and Nairn observed that we can somehow interchange harmonic analysis and topology. That is, first prove the basic results of harmonic analysis, like the regression formula and the Pontryagin theory, and then by using these results, prove the Pontryagin duality. And the idea is as follows. We already know that this map is injective and continuous. So we know that it is injective and continuous. This was proved some time ago. The next point is to show that it is a topological embedding. In here, the key role is played by the inversion formula. The inversion formula implies that if f is a sufficiently nice continuous function on G, if it is positive definite and compactly supported, then it is continuous, but its Fourier transform is also continuous. And by using this fact, we can deduce that the snap is topological embedding. This is not very hard. Maybe if we had time, we could prove it for maybe 10 minutes. Just by using the continuity of these two functions. The next step is to show that it has a closed range. That is, the canonical image of G in G double hat is closed. This is a pure topological result, which is not very hard. It states that a locally compact subgroup of a locally compact group is closed. This is locally compact, this is a locally compact subgroup, so it has to be closed. This is just the result in general topology, but it's rather easy. And the final step is to show that its range is dense. So G is closed in G double hat. Now we have to show that G is dense in G double hat. And here again, the inversion formula helps. Namely, it turns out that by using the inversion formula, we can show that L1 of G has a useful property of being regular. This means, actually this property makes sense for any commutative Banach algebra. We say that a commutative Banach algebra A is a regular if for every compact subset K, for every closed subset K let it be big F of the spectrum, and for every point X which is not in F, we can always find an element in A such that A hat vanishes on F and doesn't vanish at X. So by using the inversion formula, we can prove that L1 of G is regular. So in other words, functions in the Fourier algebra of the dual group, there are many functions in the Fourier algebra of the dual group in this sense. Now, if if we assume for a moment that G is not dense in G double hat, then we could find a function f such that its Fourier transform separates G from G double hat. So it f is a function on g hat, and its Fourier transform is a function on g double hat. It vanishes on g, but doesn't vanish identically. But this contradicts the inversion formula. That's the idea. Okay, so this is the end of our story. I'm sorry for this for not having time of proving the Pointryagin duality, but once again, I'd like to stress that this was a rather striking fact that the Pointryagin duality can be proved without using any structural theory of locally compact abelian groups. So it can be deduced entirely from the main statements of harmonic analysis. Okay, thank you.
А у локальных групп тоже есть структуры этих абелевых.
Да, они там, в общем-то, неким хитрым образом строятся там, при помощи разных конструкций, там, обратного предела и кое-чего другого из окружностей прямых, конечных групп. Вот. Ну, я сейчас несколько упрощаю, но примерно идея такая. То есть, грубо говоря, там при помощи некой длительной процедуры все более-менее сводится к двойственности Pointryagina для прямой окружности и конечных абелевых групп. Вот. Но это, в общем, все довольно непросто.